Okay, moving on to the third part, which is about the biases and robustness of MBR as compared to beam search, of course. And to give you a sense of where we are in the talk, we did talk about well-known shortcomings of NMT, the first part, and then about the potential role of beam search in causing these problems or making them worse. And now the question is, okay, if beam search is the culprit, then does an alternative to beam search, namely MBR, cause fewer of these problems? And I would argue that this question doesn't have an obvious answer. It's something that needs to be shown empirically. And so that's what this section is about. And now this section is mainly based on a paper by myself and Rico Senrich from ACL this year. So this time I'm not stealing someone else's ideas. The experiments I'm going to report on here are on the following: on length bias, experiments on copy noise and domain robustness, and the way that the experiments are set up in all of these cases is they compare the behavior of beam search and MBR and try to see if MBR has properties that are fundamentally different from the ones of beam search. So let's start with the results of length bias. So we already saw the top part of this table here, which tells us that if you look at length as the average number of tokens of sentences in a test set, then beam search translations are usually shorter than the reference translation. And I've added a row here for just sampling from the model, which indicates that simply sampling from the model leads to translations that are more similar in length to the reference than beam search translations. And basically it's just a repetition of the argument by Aikema and Aziz, for which I've shown a graph earlier. Now, what happens if you do the same experiment with MBR? And the main result of this experiment is so that the shortest possible answer is it depends, because MBR has an obvious hyperparameter, namely that it needs that a user needs to decide on a utility function that is used to compute the similarity between different hypotheses in a pool of samples. So that's an obvious hyperparameter, but also a difficult one, and so that the behavior of MBR, or whether or not it exhibits a length bias and what kind of length bias, depends largely on the kind of utility function that you use with MBR. So I have some examples here to illustrate. If you use blue as the utility function, so sentence level, a sentence level version of blue, then there happens to be a length bias in the sense that translations are also shorter than the reference translation. But on the other hand, if you use a utility function like meteor or character f, then there is length bias as well, just in the other direction, and then on average translations are too long. And the main takeaway from this experiment is yes, there is a length bias in MBR decoding as well. The bias is just different than for beam search, and it largely depends on the utility on the particular utility function you use. If you use a precision-based metric like blue, then translations will be too short. But if you use a utility function which emphasizes recall more than precision, like meteor and character F, then the translations will be too long, and so that's something that's difficult to control in MBR. Right, moving on to the second line of experiments on the robustness to copy noise. So this graph I have already shown, so that the beam search result I've already shown. To remind you what this experiment is about, it's about the sensitivity of an empty model to source copy noise in the training data. And so on the y-axis we have models trained on different training corpora that have a different fraction of the examples being copy noise. And the y-axis is just translation quality. And as I explained earlier, introducing copy noise of this sort in the training data has leads to a huge drop in translation quality. But now the surprising thing is that if you replace beam search with MBR, then the translation quality doesn't drop as quickly. So if you look, for instance, at this column again, where 10% of all training examples are copies, where which led to a huge drop in blue with beam search from above 20 to below 10. As you can see, if you simply replace beam search with MBR, then the translation quality is reduced by maybe 1 or 2 blue points only instead of 15. Again, just eyeballing from the graph. And that's something that I found quite surprising. So I wasn't expecting MBR to be much more robust against this kind of copy noise, and it confirms that beam search is partially responsible for causing the low robustness to copy noise. And here's a different view that gives a better intuition for how MBR manages to avoid copies in the translation. So and that's the first part of 2 graphs. So first of all, let's look at percent copies in translations, which is a graph I've shown before, which where I just added bars for MBR to the beam search results, which clearly shows that if you look at the percentage of translations in a test set that are copies of their inputs, then this percentage is much lower if you use MBR compared to using beam search. So let's, as always, let's look at this column where 10% of all training examples are copies. You can clearly see that in this case 50% of all the translations are copies with beam search, but almost none of them are copies with MBR. And that's where this huge disparity and difference in translation quality is coming from. And now to give an even better intuition for why MBR has an advantage, we have also shown that inside pools of hypotheses that MBR can choose from, so inside candidate translations that are sampled from the model, hypotheses that are copies, they are assigned a very low utility by MBR on average, and that's what this graph is showing. And here again, let's as always, let's look at the same column of this graph. So for instance, if 10% of all training samples are copies, you can see that all the hypotheses in pools of samples that are copies, their average utility here, I'm just trying to highlight what I'm talking about, on average is lower than the average utility of all samples in all the pools. Right, I hope I made this clear. If not, I'm very happy to explain this again in the discussion, the Q&A part. Right, and then moving on to the last point about domain robustness, where in the first part, my point was that if you take an empty model and make it translate in a domain that it wasn't trained on, then it has a huge tendency to hallucinate translations. And here as well, we were able to show that replacing beam search with MBR reduces the percentage of hallucinated translations in a translated test set. So, for instance, if you look at our test set from the subtitles domain, again, remember that medical text is our training domain. So this is an empty system trained on medical text. If you make it translate subtitled text with beam search, around 25% of all the translations are hallucinations, while if you use beam search, if you use MBR, excuse me, instead of beam search, then this reduces the number of hallucinations from 25 to around 20% only. And again, the underlying reason for how MBR achieves better domain robustness is that inside the pools of samples that MBR chooses a translation from, samples that are hallucinations, they are assigned a much lower utility on average compared to the global average of utility assigned to all the samples in all pools. So for instance, let's look at subtitles here. For instance, you can see there's a difference here between the average utility assigned to just all the candidate translations that are hallucinations compared to the global average of all samples in all pools. Right, a quick summary of this part. So first of all, and this is related to the length bias experiment. And we also have another experiment in the paper that I didn't explain about frequency bias. In general, our conclusion or our finding is that unfortunately, minimum base risk decoding does not equal minimum bias risk decoding. So MBR does exhibit some biases, has some biases as well, just different ones than beam search, and the main reason why MBR is biased, even though that the samples that it operates on are not biased, is that it uses a utility function that introduces a certain particular idiosyncratic bias. And secondly, regarding the copy noise and the domain robustness experiments, we find that MBR does increase the robustness to copies in the training data and also the robustness to domain shift as well.